It's 2 o'clock. We've had 34 of our participants involved, and we're happy to have you here. My name's Andy Albee. I am a mathematics teacher at the Adult Academic Program.
It sounds like Renee is maybe having difficulties with her muting, so I'll just go next. I'm Amy.
I'm talking. I'm sorry. Oh, sorry. Listen, a grand welcome to everybody now I'm here. This is episode 2 of the E-quip series. We are excited that so many of you are taking the time to deepen your understanding of graphs and functions, so thank you for joining us. Once again, my name is Renee Kramer, and I teach at the Renville County Jail.
I also want to welcome everyone. This is Amy Vickers, and I'm the technical support during the webinar today, so please send me a chat message if I could help you with anything. I just want to take just a little bit of time to orient you to what we're going to use with the webinar today. So we're going to have a large group. I see 37 are here. We're expecting quite a few more, and I know that some of you are participating as a group. So we'll have everybody muted, and also we will not be using the webcam feature during the webinar today. So the way to participate is via the chat feature. And I also want you to notice that you can select if you want to send a chat to the whole group, feel free to do that. Or if you would like to send an individual message to somebody, then you can do that there as well. Andy and Renee have a lot of content to cover today, so if they are not able to answer the questions that you chat in, then we'll make sure that we post those questions along with their answers in the discussion forum that will follow every E-quip episode, and those forums are on the Minnesota Literacy Council website, so you'll be able to find any additional answers that you need there. And also, I just want to let everybody know that this webinar is being recorded so that it can be viewed later by people that were not able to attend.
Okay, so today we're going to be talking about 4 topics that will be covered on the new GED 2014 test. Determining the slope of a line from a graph, equation, or table. Talking about some of the key features of graphs. Sketching graphs where we don't have to be super accurate, just getting them down, and actually graphing 2 variable linear equations. So in our E-quip webinars, some of you have already done E-quip episode 1 and you've seen this slide. What we're looking to do is try and take what sort of math do you need to know, how can you teach this to your students, and what exactly do we expect to see on the GED 2014 test. So we're looking for that little kind of nugget right there in the middle. So we're going to start. We gave you part 1, the background knowledge. Many of you took that pre-test, and that was part of that scrolling PowerPoint you had at the beginning that answered some of those questions that you had sent in to us. And we're going to build a little bit of foundation, talk about how we teach this, and then start looking towards what our next steps are.
So let's begin. Our first topic here is, what is slope? Well, slope is a number that measures the steepness of a line. In an equation, m represents slope. In addition, slope is a unit rate of a proportional relationship. And finally, as the value for slope increases, the line becomes steeper quickly. A slope of less than 1 has a more gradual incline. Thank you. Okay, so how do we find slope? There are 3 ways to find the slope of a line. The first one is, okay, I need to take controls from Andy. Just a second, I apologize. Okay, there we go. The first way is by using a graph. Depending upon which data you are given, one way or one of the 3 ways may work better than the other. So our first option with that graph then is plotting points on a graph and physically counting the units up and down, left and right to determine the ratio of the rise versus the run. Our second option is to use an equation. The first one listed, y equals mx plus b, is the slope-intercept form. It is by far the most commonly used form, partially because of how functional it is when using a graphing calculator. The second equation listed, y minus y sub 1 equals m times x minus x sub 1, or the quantity of x minus x sub 1, is in point slope form. This one is commonly used, but not as often as slope-intercept. Finally, we could use a table with ordered pairs with the slope of a line formula, which is m equals y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1, and then substitute the given coordinates in the equation to determine the slope. Before we move on to the next slide, I'd really like to talk about and familiarize ourselves with this slide. It is color coordinated on purpose. The word slope is in red, and so are the m's, since m represents slope in an equation. Secondly, the b is in blue, and it is the y-intercept, or where, like I mentioned before, the line crosses the y-axis. The green x's are the x-coordinate, or the independent value of x of an ordered pair, and whereas the yellow y's stand for the y-coordinate, or dependent value of the ordered pair. And there you have a table with all of those corresponding values for x and y. All right, so let's get a little practice here with finding slope from the graph. When I look at this graph, I see 2 points. In the first quadrant. Point B is located at 2, 3, and point A is located at 6, 4. Let's tackle the run first. Run is the horizontal distance from the first point to the second point. In this case, we count 4 units to the right of point B, so we type 4 for the denominator. Then, from the intermediate point, we count the vertical distance, which is the rise. Point A is 1 unit up, so we type a 1 in the numerator. Our slope m equals 1/4. It is important to note that as a ratio, for every 4 units to the right, we move 1 unit up. For example, for every 4 days I work, I get 1 day off. Okay, next we have the equations. So the first one we're going to look at, like I said, was slope-intercept form of the line. We have y equals mx plus b. And so our slope is whichever number value is multiplied by x. So you can see right there the red m is our slope. B is the y-intercept, and like I mentioned, that's where it crosses, the line crosses the y-axis. In the 2 pictures below, slope is important. The farmer would prefer a shallow slope, probably less than 1, if any at all, in his or her field. On the other hand, the snowboarder on the right, who is ready for black diamond runs, will be devastated to see a slope of less than 1 on a winter vacation. Okay, point slope form of a line is that second equation that I mentioned on the previous two slides ago. Once again, m equals slope, and x1, y1 are points on the line. So what we do is we can find slope where it's located, and if we have to plug slope into the equation, we know that it always is multiplied by the x. And then we have x sub 1, which is x value of our point, and y sub 1 gets plugged in or substituted into the y sub 1 in our formula. So let's talk about examples of finding slope from an equation. We have slope-intercept, and what we're going to do here is see them in real-life applications. So I could show you y equals 3x plus 7, and that really doesn't mean much of anything. But if I said to you, I wanted to take my kids and some of their friends bowling, and I needed to buy shoes for them, and if the shoes cost $3 each, that means, depending upon how many kids I have there, my x value is going to change, and so would the y value. And if the 7 represents the cost of renting the lane for all the children, because it's one of those nice places where you can put as many kids on lane as you want, then my equation is 3x plus 7. equals y, and then y will represent the cost there, and then the x would be the shoes or people. And there's my y equals mx plus b in that nice form, and then m equals 3. In the point slope form, we have y minus 4 equals negative 2 times the quantity of x minus 6. And once again, if we know how that formula is set up, we can see that negative 2 is pops out, and we know that that would equal m, which is our slope. There we go. Okay. So how to find slope given 2 points? That's our third way of finding slope. M equals y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. Where x sub 1, y sub 1, and x sub 2, y sub 2 are 2 points on the line. I think what may confuse students with using this formula, or at least at times it's confusing for me, and maybe it's just me, but if I just look at them and I plot them in, then it's just fine. But when I try to figure it out and put it with the table, I think what confuses them is x sub 1, y sub 1 in parentheses, and what x sub 2, y sub 2 in parentheses, like they're shown in the sentence part right there. They are horizontally connected. Then when they see this, when they use the formula, the ordered pairs change their orientation and now are spatially connected vertically. You see to the left of the sentence, right here, they're actually up, vertical from one another. And so I think if we can point that out to our students, I think it helps them to understand that it's not really in order that it's written out. And also that the pair listed last, this x sub 2, y sub 2, actually ends up becoming the first fraction per se in the y in the formula there. So let's continue. So how to find slopes from a table? We have a table right there. We have our x values and our y values. Let's go ahead and use our x sub 1, y sub 1 as 2, 0 there. And then our second order pair, x sub 2, y sub 2, 5 and 6. And we get ready to plot them in. So here we have our y sub 2 and our y sub 1 that we pulled off of the table here. And then our 5 minus 2 for x sub 2 minus x sub 1, and it's going to go ahead and be 6 when we subtract, and be 3 on the bottom, the denominator when we subtract, so our slope then becomes 2. And we keep stealing the controls.
Yes, were you wanting to show them how to do that on the calculator?
Yes, sorry.
Okay.
So we go ahead and we type in, let me get back to the, there we go. It's right there in the big letter too. 6 minus 0. So we'll go ahead and
clear. Remember, we can do the fraction key right over here. And when we get that, you'll see the fraction right in the calculator. And you can enter in the materials just as you see them. So the 6 minus 0, we'll do 6 minus 0. And then to get to the next one, we hit the down arrow to put us down in the denominator. And remember, your students will have this available to them on the new test. 5 minus 2. And then we can hit the enter, and they'll just go ahead and give us the 2. Okay, and you can have controls back.
thank you. Sorry about that. I'm glad you stepped in. Okay, so how will this look on the GED 2014? We have a question here that many of you may have already looked at if you took the sampler. The painter rented a wallpaper steamer at 9 a.m. and returned it at 4 p.m. He paid a total of $28.84. What was the rental cost per hour? So let's look at the formula here. m equals delta y over delta x, and then delta just means the change in those y values and the change in the x values. So at the end of renting the steamer from 9 to 4, which is 7 hours, the painter has to pay $28.84. At the start of the day, he had 0 hours rented and owed nothing. The change then is $28.84 from $0 and 7 hours from 0 hours. So since when you subtract 0 from something, you still end up with the number you started with, we divide that, and our quotient is $4.12 an hour. That means that for every hour that he rented the steamer, he has to pay $4.12 more than the previous hour. So x in this case is his independent value, or our independent value, which, and the reason why it's independent is the painter gets to pick how many hours he or she, or he in this case, wants to rent it. So he gets to choose whether or not it's 0 hours or even more. And then we have the dependent value, the y, was the cost, which is told to the painter. The painter doesn't get to choose how much he has to pay. It goes per how many hours he rented it. So that is automatically determined by the hours rented. In this instance, as x, the hours increases, y, the cost increases. This problem highlights the proportional relationship of slope. And so that's why we put it in here. And I'll advance the slide. So let's check in here. I'm going to launch a just short quiz for you, and please answer the questions, and then raise your hand when it is done.
Okay, we've got a few of you that have raised your hands. We'll wait just a little bit longer. There's a few more. Okay, about 15 seconds. We'll go ahead and close the quiz. There we go. I think we got a pretty good level now. So there you can see everybody, 91% of you answered correctly that M is slope for those that answered. And 57 found that the slope of that equation was 14. Remember, the slope is what's multiplied by the x. Okay, so I'm going to take a little bit here and talk about, Renee did a fantastic job of coming through of what slope is, how we find it in the equations. Everybody seemed to have a fairly good hold there. But we're going to talk about what does slope really mean and how do we teach this. For me, the way that I try and teach it to my students is to get them to think about riding a bicycle. Slope is just how fast one variable is changing in relationship to the other, our dependent variable to our independent variable. And the way that we can visualize that is imagine riding a bicycle uphill or maybe riding a bicycle downhill, and how steep is it. Maybe you're here in Minneapolis and riding it nice and flat, because we don't have a whole lot of mountains here, or you're the wild daredevil over here just kind of jumping off into the middle of nowhere. So how do we interpret what positive slope is? Positive slope means as x goes up, as our independent variable goes up, so does our y variable or our dependent variable. Really good example of this the students are going to see every day is gas prices. So if gas costs $3.25.9 a gallon, the more gas you buy, the more money you pay. And obviously if you buy less gas, you pay less money. So as X goes up, as the number of gallons goes up, the cost of what you're buying goes up as well. So I've drawn that line on a coordinate grid graph, and you can see my little bicyclist here. And as we go from right to left, you can see that he's going uphill. So that helps him to see that that's a positive slope. So the question is in this graph, is this thing a function? We asked you to do some work on what functions are and how they interact in the pre-webinar service, and on the pre-scrolling thing we talked about what a function is. So if we look at this, we want to check, can we make this into a function, get an equation for it? Remember, our slope is our change in our dependent variable as compared to our change in the independent variable. Our variables here are dependent. Instead of using y, I've used p because we're talking about the price of gas. And instead of using x, I've used g, the amount of gas you've actually pumped. So a nice connection here is that it doesn't have to be y and x. We just kind of generally usually do. And for us here, our slope is $3.25.9 per 1 gallon. Yes, this is a function. Okay, we can check it by doing the vertical line test. If I draw a line up at 6 gallons, it's going to cost me around $20. And there's one output for the one input. There's our equation if we had written it out as an equation. So what about a negative slope? Well, a negative slope means as your independent variable, like x, goes up, then your dependent variable, y, goes down. I did an example of draining a swimming pool here. And if we drain a swimming pool and we're draining out 5 gallons every 1 minute, the longer you drain the pool, the less water is left in the pool. So here's that graph, and I started this with a pool that starts with 60 gallons in the pool before we start draining it. Again, the bicyclist on the line, and if we look at him from left to right, he's going downhill now. Is this also a function? Well, if it is, we ought to be able to calculate a slope and get some values out of it. So there's our slope equation, the delta y over delta x, dependent versus independent. This time, instead of x and y, I've used w and t to talk about how much water is in the pool and how much time has elapsed. And so our slope in this case is 5 gallons leaving the pool every 1 minute. And yes, this is a function as well. If I can see here at about 6 minutes, I should have around 30 gallons left in the pool. Our equation would have been w equals negative 5t plus 60. Or if you wanted to be more comfortable with the y's and the x's, you could have y equals negative 5x plus 60. It would have been just fine. So what is something that could have a zero slope? The next two, the zero slope and undefined slope, are ones that tend to kind of have a little bit more confusion for the students. A really nice one, a good example for the students to bring in, is checking the length of a ruler. No matter when you check the length of a ruler, this year, next month, doesn't anything, a ruler is 12 inches long. It doesn't change length. So if we had, sorry, I clicked on the ruler. Okay, I'm not clicking on the ruler. There it goes. If we talk about a graph of the length of the ruler and time being my elapsed time, notice the bicyclist, as he starts to ride, he's going nice and flat. He's not going up. He's not going down. There is no vertical change. So is this a function? Well, if we can calculate our slope, our change in length of the ruler divided by the change in time, which I in this case called r and t, we can see that the ruler length does not change. And down here at the bottom, I put delta t does not equal 0. The important idea here is for this to be a slope, there has to be some change to it. There has to be two different points. If I select year 0 and year 5, my length change of the ruler doesn't change. It's still 12 inches. But my time change did change. It was 5 years later. Okay. Is this a function? Yes, it is. Still same thing, vertical line test. No matter where we choose, it's 12 inches, and our equation would be r equals 0t plus 12, or r equals 0x plus 12. The last of the four is by far the trickiest one for the students to figure out, and that's what happens if we have this thing called undefined. The undefined slope says as x stays constant, as our independent variable doesn't change, our dependent variable, y, does change. So imagine buying 2 bags of apples, and one person goes in and buys a bag 3 pounds worth of apples and pays $6. And the next person comes in and buys the exact same 3-pound bag of apples, but they say, we're going to charge you $10 instead of the $6. You just look like you can afford more. Okay? Our cost of the 3 pounds of apples then the cost changes while the amount of apples, the weight of apples, does not change. You see our bicyclist over here, and he's trying to ride on the slope, and he doesn't. He falls right off the side. Okay? So if our bicyclist can't ride on it because it's just a cliff, that is an undefined slope. So is this a function? Well, if it's a function, we ought to be able to find a slope. Remembering our slope is our change in y over change in x, or our change in dependent over change in independent. Our dependent variable now is our cost. How much does it cost to buy the apples? Our independent is the weight of the apples that we're buying. And in this case, the cost change is not 0. One person paid $6, another person paid $10. But the weight did not change. Okay? This can't happen. This would be really bad if you tried to go into the store and buy apples this way, because you wouldn't know how much to pay for your apples. Is this a function? No, it is not. It fails that vertical line test. If I choose on 3 here and I go up, I hit multiple points where that function has an output. So for a function, for every variable, every value down here in the x's, or in this case the a's, there has to be one and only one value of the y's, or in this case c's. Oh, sorry. Extra slide. We're going to kick this one out. There we go. So if we can calculate slopes and know what slopes really mean, there's 2 other pieces that we're trying to make sure that we help the students understand. And those are the intercepts and the possible values. And there's some special names I'm going to give to the possible values here. I'm going to come back to that gallons of water in the pool graph that we were doing earlier. And the amount of water in the pool started right up here at 60. That's our y-intercept. There's 60 gallons in the pool when we haven't drained it at all, at time 0. So at time 0, the water in the pool is 60 gallons. If I try to find where it hits the x-axis, or in this case, the t-axis for time, that intercept is about 12 minutes, which means if we're emptying the pool at a rate of 5 gallons every minute, after 12 minutes, there will be 0 gallons left in the pool. Okay? Those gives us where those hit the axes. Well, what's in between them then? What's in between them is what we call the domain and the range. The domain are the possible values of our independent variable, in this case time, which for our pool example was 0. We could start at we haven't drained the pool at all, but after we've drained the pool for 12 minutes, there's no point in continuing to time ourselves because the pool is empty. So the value of the domain, the possible values in here, are anything from 0 minutes to 12 minutes. But if we have the domain, what can go in for the independent variable? We also have the range, what can go in for the dependent variable. In this case, the amount of water in the pool depends upon how long we drain it. And we could have started at 60 gallons in the pool, but the longer we drain the water out of the pool, the less water is left in it until such time as there's actually 0 gallons left. So once we know our intercepts and our possible values, our domain and our range, we want to be able to just kind of quickly sketch out a graph. So I'm going to sketch one here in quadrant 1, which was one of the things that was in the pre-webinar PowerPoint that was up. And we're also going to do one in the other quadrants as well. I'm going to say, suppose that Vanessa put $50 into a retirement account. And she's not going to retire on that. Hopefully she's going to put in more. But she earns 3% interest. Okay? How much is in her account? Well, how much money she has in her account depends on how much time she leaves in there. The more time, more money. So time is going to be our independent variable. That will go on our horizontal axis. The amount that's in her account will be on the vertical axis. And somewhere in here, we're just going to sketch a line showing that that value is, at 3% interest, going to grow. It's not going to grow real fast, but it will grow. Notice there was no scale on here. We didn't put on anything as far as, this is exactly 50 or how many years or time we have on here. Just in general, this graph is going to gently rise. Okay, but what if we have something that's outside of just quadrant 1 where everything's positive and we have something that might be a little bit negative? So what if Johan has $2,500 left in his college savings account? Okay, so he's going to college, he's saved up some money, he's got some money left. We want to know how much does he have in his account, or how much does he have to borrow if he needs to pay $300 per credit? Well, based off of that, the credits taken, how many credits he's taking, will be our independent variable. He can choose that. But after he's chosen to take credits, the amount in his account is what will depend upon that. Noticing here that we start with some money in the savings account, the $2,500. So our y-intercept has to be somewhere above 0. And since he's spending $300 per credit, each credit he takes, and he's going to have less money left in that account, our slope is a negative 300 per credit, or in other words, it's kind of generally going down. At some point out here, and in this case it would be a little bit more than 8 credits, he's going to have to start borrowing money. And so he's going to have negative values. We could have also said that before we started checking this $2,500 left, if he had some money in there prior, but he's already taken some classes, he would have had more money available in that account before he paid for the classes he took last semester. So we could have negative credits taken, the ones he took before, and a negative value, he owes money in loans. Okay? So I'm going to do a quick check-in on our graphs. Unfortunately, our testing structure in the webinar does not allow us to have graphs in the choices. So I'm going to have you study this, and when you're ready to take the test, I want you to raise your hand so I can pull up the test, and you'll select A, B, C, or D. So suppose that Aaron set up a snow removal service for his neighborhood. He went out and bought a used snow thrower for $100, and he plans to charge $20 per driveway. What would be his profit or loss for him to run this service? Okay, so again, please raise your hand when you're ready for me to start the test. Sorry, back up. I forgot to freeze the screen before I did that. My fault. Okay. Seeing about 12 or so hands up, so I'm going to go ahead and launch the test, and then we'll do that on there for about 10 seconds because you should have already made your answer. Amy, it's locking up on me there. Okay, so here's the test. And yes, 89% of you did answer correctly. That in here, the line B means he had to start with a negative value. He had to pay that $100 to start with, and then his profit increased by that slope of 20%. Okay, so good job, everybody. We're going to hide this back off, get back into the presentation, and give it back to Renee.
All right, thank you.
Okay, there you go.
So what will this look like on the test? Okay, let's see, from current slide. There we go. All right. The scientist, let's read this problem, and many of you might have seen this before because it's part of the sampler. But it says a scientist is studying red maple tree growth in a state park. She measured the trunk diameters of a sample of trees in the same month every other year. The tables show the data for the two trees. This is the final year in which she will collect data. When her data collection is complete, she will predict future red maple tree growth. The scientist plots the data for tree 2 on a coordinate grid. She begins by plotting data for year 3 and year 11. What are the locations of the 2 points on the coordinate grid? So click on the grid to plot the points. So we need to figure out what is actually important here. So we know that we need to look in the column or in the chart for tree 2 because tree 1 really is irrelevant, and we need to make sure students read carefully enough to realize that. We look at year 3 because that's what the question asks us about, and same with year 11. And so if we can help our students to realize that that left column of that chart is actually our independent value, and the right column and the diameter in the trunk, that's our dependent value, because depending upon how long she waits to measure them, she gets to choose when she measures. She does not get to choose how much the tree grows in the meantime. And so that means that the year is the independent, which is the x value, and the diameter is the y value of the dependent. So we'll go ahead and figure out how to plot these points. So we look, and once again, like I said, the year is the x value, so we go over to the right 3 units and up 12. And we put our dot right there to plot that point. And then we go down to the other ordered pair, 14.4. We go over to the 11 and up to 14.4, and we plot our point right there. So that's exactly the whole problem. That's what our students would have to answer. But we like this problem so much that we wanted to expand on everything. So let's continue with that. There's our line right there to connect them. So how will we figure out the slope of this graph if necessary from the graph? So if we remember that our equation for finding the slope from a graph would be m equals rise over run. So we're going to look at the run first, and we see that it moves to the right 8. So we put 8 years in the denominator, and then it goes up 2.4, that's our rise. And when we divide that, 2.4 divided by 8 equals 0.3 or 3/10 of an inch per year. So for every year that she waits to measure, the tree should have grown 3 inches. So that would definitely be a proportional relationship because they change together. Without the time, the tree can't grow, and vice versa. So, and then we look at it too from the graph, from the angle of a table. So we have m equals y2 minus y1 over x sub 2 minus x sub 1. So here's where we make sure that we're pulling the right numbers from our table and putting them in the right spots in the division problem here after we subtract. So 14.4 minus the 12.0, which 14.4, those are dependent values. So those will get put down there on the top. And right here we have 11 minus 3, which comes from the x values here. And we do our subtraction. And we get, once again, 2.4 over 8, and we divide. and it grows 3/10 of an inch every year. So for every year, the tree grows 3/10 of an inch, and that's our proportional relationship. So let's check in once again, and we'll have our test here going on. See if I can get this moving so you can take that. And please raise your hand once you're done so that I know you're done. Okay, about half of you have responded, and we'll wait a little bit longer to let everybody get a chance to finish. We're at 3/4 done, finished. All right, I'm going to give you about 10 more seconds, and then I'm going to close the test. And we're going to review it. There we go. All right, find the slope of a line that passes through this pair of points, -3, 3, and -2, 0. So it looks like 70% of you had the correct answer of 3. Let's go back to the PowerPoint then, and we'll look at that some more. There we go. Okay, the explanation. So if we have points -3, -3, and -2, 0, we have our y sub 2 minus our y sub 1. So once again, we look at, here's our y sub 2, which is 0, and then here's our y sub, or excuse me, y sub 1, which is -3. And what ends up happening is that we put those here in the numerator. Well, when we subtract a negative number, it's just like adding it, so that becomes a +3. And then our x sub 2 is -2, which is right there. And then our x sub 1 is -3, so we plot those into the equation. -2 subtract a -3, that's going to become a positive as well. So we end up with 1 in our denominator, and so our slope equals 3. So here we have our post-webinar follow-up. So what could this look like in your context? We have, I'd like you to please consider one thing that you learned during this episode and how would it look in your classroom. We also wanted to let you know that we as facilitators, Andy and I, will be available for 1 week to respond to any questions or comments you may have online, and then those conversations will be archived. The resources and the webinar will be available on the Atlas website soon, and we would truly like to thank you for your participation today. We hope that you can join us for the next episode.
And noting that the number 2 that we'll be able to respond to your questions and comments, you will get a follow-up email after we're done here that will tell you how to get to those activities to be able to follow up with us.
Mm-hmm.
And noting that, oh, go ahead.
Well, I was just going to mention here real quick that the E-quip Math PD series today, we had ours. There's already, so that will be archived soon. The first episode is available at the site listed there. The other 3 E-quip Math PD series webinars are Connecting Coordinates, Lines, and Equations, which is on Wednesday, November 20th, and As of right now, the registration is open. It's from 3 until 4 o'clock, so hopefully you'll be able to join that with us or with the presenters. The fourth one is solving quadratic equations, which will take place on Monday, December 2nd from 3:30 to 4:30. And the fifth one is finding surface area and its related dimensions on Tuesday, December 7th from 3 until 4 in the afternoon. Once again, I'd like to thank you for attending today. We hope that you have refreshed and or added to your knowledge of graphs and functions. On behalf of your current and future students, we say thank you as well. Have a great weekend.
We do have a little bit of time. This webinar went just perfectly, I think, on our timeline. So if any of you have a quick question that you'd like to ask and want to be unmuted in order to ask it, if you just want to raise your hand, or remember you can always chat if you have any questions. So, if you have anything you want to talk about, we have a few minutes to talk about things if you'd like.
So, Luella, is your hand raised? I unmuted you if you'd like to ask a question.
Could you re-review the point slope form?
Yep, we'll do that in just one moment. Okay. Okay, so the point slope form, that was that y minus y1 equals m times the quantity x minus x1. We'll back up to that slide here. Actually, I'm just going to do this. Okay. In our y minus y1 equals m times x minus x1, remember that x1, y1 are simply a point on a line, something that they gave you. In that tree problem, it would be like the third year and the 12 inches diameter. The m is the rate of change. It's that slope. So when we calculated on that tree, it was the 0.3 inches per year once we calculated out the slope. Sorry, I have to get this back up there too. So Luella, I'm going to unmute you here again. Okay, did that help any, or was that beneficial for you?
Well, there was this one where you guys were talking about given the slope and the point, but what could we, if we're looking for another xy value, is that what this is for?
Yes. So the question that we had down in the tree question, for example, I keep running back to that one, but we had year 3, 12.0 inches, and year 11, 14.4 inches.
Okay.
They might have asked, what would you expect on year 15? Or what would you expect it on year 17, or something that's outside of our chart? So if we were looking at that, if you put it into your y minus y1, we don't have that on that slide. If you put it in the y minus y1 equals m times x minus x1 form, where m would be that 0.3,
Okay.
and y1 could be either the 14.4 or the 12.0, either one. But if you choose the 12.0, for example, as your y1, then you have to choose the 3 as your x1. And if you plug those two coordinates, the 3 and 2.0, into the equation along with the 0.3 inches per year of slope, then you could calculate for any other year even beyond the end of our table.
All right.
Okay?
Got it.
Do we have a way we can visibly show her that? I mean, would that tablet work to do that right now or not?
Let me see if I can do that. Okay. Well, tablet's giving me control, but it's not giving. Oh, wait a minute. Pen. Pen. Okay. Hey, it works. So we're going to come over to this one so I can get to a cleaner one.
There's that one empty slide.
There's an empty slide.
Remember? Right before that first GD question?
Oh, that was the GD question that it didn't advance yet.
Okay.
But that's okay. Let's just do it right on this one because I can do it here. Well, or we'll go to that one. We can just erase all drawings, and we'll go back to our tree. Okay. If we looked here, put that back where it's supposed to be, at our equation, if we wanted to write this as an equation, we could write y minus the y1 value that we would have. Let's go ahead and pick the 12.0 equals our slope, which was our 0.3, 3/10 of an inch per year, times the quantity, and we would do x minus the x1 that was involved with that y1 equation up here, which was 12.0. Our x1 then would be 3. And that would be our equation. And then if we said, well, what would you expect the tree to look like after year 17? You would just let your independent variable, x, equal 17 and just plug it right into that equation. So you'd have the 17 minus 3 would give you 14, times 0.3 would be 4.2, and then you'd have to add this 12.0 over to the other side to get y by itself. And if we did that, we would have 16.2. So at year 17, we would expect the tree to be 16.2 inches in diameter. Okay, does that help with showing how that formula would be used?
Yep.
So this is just basically an inverse formula of the other one.
Yeah, it comes from the slope equation. You know that we have here that y2 minus y1 over x2 minus x1 equals the slope. And I know there's those little 2's there. That's our animations. Yeah, we can do another one. That's just fine, Clarice. But if we take these and just multiplied by x2, x1 on both sides, and then just allowed y2 and x2 to float and just become y and x instead of y2 and x2.
Okay.
Okay. What if we had our Aaron question? Okay. If we looked here at this one, we will erase all drawings. We could say that we know that at select pen. At number of driveways 0, before he's even gotten anybody to sign up to allow him to clear their driveway, he has spent $100 because he had to buy the snow thrower before he could even start his business. Now from there, he went on and charged a rate, a slope of $20 per each one driveway. Okay? So if we put this into our slope-intercept equation or our point-slope equation, we could say that y minus a negative 100, because we're going to use the y value from this point that we were told. And that would equal the $20 per driveway, the slope, times the number of driveways that he's going to snow throw minus his starting position, but his starting position in this case was 0. When he started the business, he didn't have anybody signed up. And so there is our point slope form. We have a point, negative 100, and a point 0, the two coordinates of that one point. and we had a slope. We knew that he was changing at a rate of $20 per driveway. Okay, so there's a couple of examples of how that could go. The other one that you could do is we did have that y equals mx plus b. Remembering that m is our slope, so that's the exact same one, y equals 20x. But our plus b, the b is the initial condition. It's what is the value when our independent variable is 0. Well, we know that one because we started off with 0 here. And so we can just put in here, right here, plus the x or the y value of this point, negative 100. Sorry, I kind of got myself ran into each other there. And y equals 20x minus 100 plus a negative 100, same as minus 100. This is $100 in the hole. If he gets one driveway to clear off, he's still going to be $80 in the hole. He hasn't paid off his snow thrower yet. If he got 4, he will have made $80, but he still hasn't paid off that $100 yet. If he got 10 driveways that he's clearing, he's going to make $200, but he had to pay out the $100 to buy the snow thrower, so he's made a profit of $100. Okay, we're just about out of time. I'm going to go ahead and unmute everybody. If you have a question, I know it's a lot to throw a lot of people in here. Oh boy, that didn't work.
Muted.
If you had anything else that you wanted to talk about or any quick question we can do in the next couple of minutes, go ahead and raise your hand. I'll unmute you. And remember, you can always use the chat here as well. So yes, Amy also brought up the fact that in the next webinar, we're also going to be working with graph slopes, coordinates, etc. If you would like more help on this, Rebecca and Amber are going to be absolutely fantastic in that webinar. Please do go ahead and sign yourself up. Okay, and I'm not seeing any other hands raised, so I'm going to go ahead and